Well, Parker, I just want to thank you and your team so much for organizing, this Space Apps Genius Summit. From what I was just talking with Parker, I've heard there's been some amazing sessions that have been taking place over the last, day and a half, whatever, however long it's been. So I want to thank Parker, you and your team, and also I want to thank everybody that is joining today, wherever you're joining from. If it's, could be in Asia or Africa or Europe or South America, etc. I just want to welcome you all to this session. My name is Sean McCartney, and I am a representative from the Applied Remote Sensing Training Program. And today I'm going to be talking to you about the practical applications of Earth observations. Great. And I'm just going to briefly stop. I just want to, great. Okay, now I'm back. Great. And moving forward. So NASA has a long and storied history of exploration and innovation. For those that are seeing this, we can see that NASA's mission is to explore the unknown in air and space and to innovate for the benefit of humanity, regardless of what country you come from, and also to inspire the world through discovery. The image that you're seeing here shows the NASA Science Fleet. This is all different missions that NASA is currently operating and will be launching soon in the future. It is the largest civilian satellite fleet in the world. But you'll notice if you look toward the bottom left of the screen, you can see that we have this beautiful planet Earth, and we can see that most of the missions are actually involved in observing our own planet. So they're actually looking down, not looking out, as they might be if you're, say, a space telescope.
Hello? We can't see your screen anymore. If you mind resharing. Sorry about interrupting.
Okay, interesting. Interesting. Okay. Thank you for whoever mentioned that. I don't know why. Are you seeing it now?
There we go. Yes.
Okay, interesting. I apologize for that. I don't know why you couldn't, but hopefully you're seeing it now.
Looks
So okay, great. Thank you so much. And then, so if you'll notice that there's a lot of different images on the screen. In the upper left, we have we can see galaxy, and we can see a lot of the heliophysics missions. We can see on the right, we can see our sun and some of the heliophysics missions that NASA does. In the bottom right, we can see some of the planetary missions. But as I was just saying, in the bottom left, we can see that the majority of NASA missions, the NASA fleet, is actually looking down at our own planet. So NASA studies all of our planet, and just like our own bodies, the Earth is made up of very different systems that interact in complex ways. So for an example, heat can be absorbed by the ocean, and that increase in ocean temperature can be transported somewhere cooler by ocean currents. There, that heat can be released into the atmosphere, influencing weather patterns by forming clouds and rain. Rain impacts the availability of water and soil moisture, which affects the health of plants and of crops. So NASA, we have to study the whole picture to not only observe what is changing, but also understand how changes in one of these systems impacts all of the others. So NASA Earth science has to be end to end, from developing the technology to monitor our world to ensuring decision makers have the skills they need to actually use that information, and every step in between. That process looks something like this. So starting on the left, we have the technology that develops the next generation instruments, communication systems, and computer modeling. And then we have flight, and which represents the satellites and the aircraft missions, as well as the different platforms that we use, that we place these instruments upon. Then we have the research and analysis, which is taking these observations and modeling and turns them into understanding about our Earth system and interaction between the processes, the data, and processes going on the planet. And then we have the data and compute, which oversees the life cycle of NASA data from the acquisition to the processing to delivery. And finally, on the right of the slide, we can see Earth Action. And that, I believe you already heard from Emily Salak-Glisman, and she probably represented NASA's Earth Action program. But that is to help people around the world use NASA Earth science data to inform crucial decision-making, enhance quality of life, and strengthen our economy. So rather than a one-way flow, this work connects back to one another so that we can feed back what we learn in one element to those in other parts of Earth science. So today I'm here as part of NASA's Earth Science Applied Sciences program, which is now known as Earth Action. Earth Action provides support and funding to help institutions and individuals make better decisions about their environment. It does this through thematic program areas, as seen on the right-hand side of the slide, covering everything from agriculture, climate and resilience, disasters, ecological conservation, health and air quality, water resources, and wildland fires. Each of these is a program where scientific research focuses on helping decision makers within that given theme. This visualization is showing our current satellite fleet dedicated to observing our planet Earth. We have over 25 missions orbiting the planet, with more launching even this year. In a few months, we'll be launching the NISAR mission. Hopefully somebody is already spoken to you about that over the course of this this Genius Summit. But if not, just know that NASA and its partnering space agencies are constantly launching new missions to better observe and monitor the changing processes taking place everywhere from the atmosphere to the biosphere and the hydrosphere. And 10 satellites in this example are make up the global precipitation measurement constellation. In this animation, you can see the constellation in action and the precipitation measurements taken by each satellite. Over time, the entire Earth is mapped, and we get a global view of precipitation. We can see the relatively constant rainfall patterns along the equator and storm fronts further toward the poles. We combine all this information from these satellites to create a product called iMerge. The iMerge product offers global precipitation every 30 minutes. In this image is the US Department of Agriculture, which is taking data from the Landsat missions, in this case from 2020, the year 2020, and it's monitoring crops across the United States, in this case being the contiguous United States. This information is used to track how many acres and the annual yield for every crop produced. The colors on the right-hand side in this, the legend, are showing the top 10 of the top 20 crops grown in the contiguous US in the year 2020. And this is all data that everybody here on this call, this workshop today can get access to for free. And information from satellites is also used to study and monitor fires and smoke. Each dot in this animation is a fire that has been detected by satellites, and they are colored by how intense they are. So more intense fires are shown in light yellow or white. It's likely that everyone in this workshop at some point has been impacted by smoke and from wildfires. Observations from NASA satellites not only tell us where fires are burning globally in real time, they also provide information on how smoke from fires affects air quality in communities impacted by these fires. And looking at satellite information over time can also show us the impacts from federal environmental laws like the Clean Air Act, which was signed in 1970. So nitrogen dioxide, or NO2, is a pollutant that is produced during the combustion of gasoline in vehicle engines and coal power plants. NO2 can negatively impact respiratory system, and it also contributes to the formation of other pollutants, including ozone. Air pollution is the fourth leading cause of death worldwide. Only high blood pressure, tobacco use, and poor diet kill more people. In this animation, high levels of NO2 are shown in pinks and purples. The satellite observations show that NO2 has decreased 40 to 60% since 2005, even though the number of cars on the road during this time have actually increased. This decrease is likely the result of regulations and technology improvements. So for the agenda for what I'm hoping to cover in this workshop is the next group of slides. We're going to discuss the program in which I represent, which is the Applied Remote Sensing Training Program. From there, I will move into a fundamentals of remote sensing section where I'll cover some of the fundamentals you'll need to be able to understand and work with different satellite data and derived products. Then I'll show some training examples that ARSET, this program, this applied remote sensing training program, I'll show some examples of different trainings that might be of interest to you. And then as well, some case studies that we've done during these trainings, these ARSET trainings. And then I really want you to be able to interact with some of the NASA data. So there's going to be a component toward the end of this workshop where I'm going to give everybody on this session the opportunity to access NASA Worldview and start interacting with the data, so you can see how you can start mapping and visualizing these different data sets. And then we'll have a summary, and lastly, we'll do a question and answer before we wrap up. So quickly, I'd like to tell you about the Applied Remote Sensing Training Program, which is the program in which I represent. We provide accessible, relevant, and cost-free training on remote sensing satellites, sensors, methods, and tools. And this is for anybody on the planet. As long as you have an internet connection and you register for one of our trainings, you will be registered and you'll be able to participate. And trainings include a variety of applications, and these applications fall within the themes that you see on the right of this slide. So for example, we do trainings on agriculture, disasters, water resources, everything on the right of the slide. We'll do trainings, but not just within these thematic areas. We are an applied training program. So we're not just trying to tell you, okay, this is where you get the data and what. We also walk you through a workflow of an analysis that you can do with these data sets using open source and open access software so that you can derive in your own study area and for your own area of interest and time period, you can come up with results that can better inform you for better environmental decision making. And our strategic goal ultimately is to enhance the use of Earth observations in decision making. And that decision making can be for anybody on the planet. And so why do we provide remote sensing training? Well, if we look at this graphic on the right, we can see that a lot of people aren't even aware, first off, that NASA has an Earth Science Division and that the majority of NASA missions are actually studying our own planet. So first, we want to build that base level awareness of what NASA datasets and modeled products are able to provide to the user community. And once we build that awareness, then we want to dig a little deeper and build an appreciation for the applications one can do with these different data sets. And once we have an appreciation, we really want to build that appetite because we want you to say, hey, if I can use the data set for this application, I can probably use it for this other application in a different domain or area of interest. And finally, we want the adoption of NASA data. There is a huge investment from US taxpayers to build these missions, to launch them, and to keep them flying and collecting this data. But none of that is of any value unless you, the community, are taking that data and applying it in your own, in your research or on professional work. So we're really hoping that the ARSET program is able to have that impact and get people to not only have an awareness, but an appetite to use the data. This is a slide from 2009 when ARSET was founded to last year, 2024. So these statistics are everything except for the current year in which we're in. We can see that we've trained over 145,000 participants from all over the world, the majority of our participants coming from the United States, a lot from Canada. We have a large user base in South America, and that's because a lot of our trainings are actually bilingual in Spanish, but you can see from this map, we certainly have coverage from all over the planet. So hopefully you can see, if you're joining us from somewhere else outside of the United States, wherever that might be, hopefully you can see yourself reflected in this. And we do hope, if you haven't taken in ARSET training, please do sign up on our listserv. Our trainings are both online and in person. So they're live and instructor-led or asynchronous and self-paced. They're all free, there's no cost, and we only use open source software and data. So only publicly, freely available software and data. And all of the materials are translated into Spanish, but we also have some trainings that also, we've had some trainings in French as well. And we also accommodate different levels of expertise. So for example, if you look at the bottom of this slide, you can see the fundamentals training. And we actually just released a brand new fundamentals of remote sensing training. It is a self-paced guided training. It's modular, so you can complete part of that training and come back to it at a later time. But that's for people that might not have had any background in remote sensing. And then from there, we have a higher level of training, which is an introductory, where we're really trying to cover broad applications and show people where they can access that data and demonstrate different case studies. Intermediate trainings, which are a little bit higher on this increasing knowledge and skills, they require more specific applications, and there's probably going to be a higher level of expertise. So you're probably going to be working with the data yourself. And then as we go to advanced trainings, the expectation is you are going to adopt the the workflow and the case studies in which we're showing, and you are going to take those methods and workflow and really apply them in your own area of interest. And then if you want a certificate for attending the training, then you would have to show through the homework that you had executed that application in your own area of interest. So we have diverse content to suit different training needs. So we have lectures, and I'll be providing a lecture momentarily on the fundamentals of remote sensing, but we also show demonstrations which show how you can really use this data in different application areas. Then we have hands-on exercises, which depending on the level of training, if it's introductory versus intermediate versus advanced, these hands-on exercises will be more technically difficult for participants to follow. And we also have homework associated with every training. And we also have a question and answer session where we have subject matter experts in atmospheric chemists. We have agricultural engineers. We have different people that at the end of the training you can ask and post your questions so that we can answer them in real time. And at the end of every training we also have an evaluation so that we can always improve upon these trainings going forward. So the next level of next session in this workshop, we're going to be covering a broad fundamentals of remote sensing. So if you maybe are new to this discipline, hopefully this is going to be of value. Before we move on to the next session, some of this might be a refresher. For some of you, you might know this because you deal with remote sensing every day, but this is more targeted to people who might be new to remote sensing and wanting to learn more about the theory and the fundamentals to it. So, so to start out, remote sensing at its main definition is obtaining information about an object without physical contact with it. I want you all to think about something you use every day that is a remote sensor. Maybe just take a few seconds and just think about things that you interact with any given day that might be something that you obtain information about without actually physically touching it. So some of you might be thinking about, say, the camera on your smartphone, or maybe some of you are thinking about your own eyes, deriving information about your situational awareness, about your environment, your surroundings, without actually touching any of it. These are all examples of remote sensors. And there are many different ways to collect information, and different sensors or instruments are used depending on the application. So some methods include ground-based remote sensing instruments. Some are ocean-based. Some are airborne, so they're on planes or aerial platforms such as drones or unmanned aerial vehicles. And then we also have spaceborne platforms which collect remotely sensed data. So the questions really one needs to ask prior to any data collection, and this doesn't matter if it's on the ground in a field or if you're collecting it from a satellite, the questions you need to ask are, what information are you ultimately trying to get? How much detail do you need in that information? And lastly, how frequently do you need the data? And remote sensors, the primary source of energy for remote sensing received on Earth is the electromagnetic radiation from the sun. So radiation is reflected, absorbed, and emitted by the Earth's atmosphere or surface, as we can see in the figure on the left of the slide. The amount of the sun's energy reflected depends on the roughness of the surface and its albedo. And albedo really refers to how well a surface reflects light instead of absorbing it. So snow, for example, has a very high albedo or reflectance and reflects up to 90% of incoming solar radiation. The ocean, on the other hand, reflects only about 6% of incoming solar radiation and absorbs the rest of that radiation. And often when energy is absorbed, it is re-emitted, usually at longer wavelengths. So for example, the energy absorbed by the ocean gets re-emitted as infrared radiation, even though it might have been absorbed as visible light. So the human eye can only perceive radiation within a limited range of the electromagnetic spectrum. So instruments for remote sensing outside the visible wavelengths actually represent an extension of our visual field that we see with our own eyes. And they give access to additional information about the physical world surrounding us. Satellites, they carry these instruments or these sensors that measure electromagnetic radiation reflected or emitted from both terrestrial and atmospheric sources. And with calibrated instruments, scientists can measure the height, temperature, moisture content, and more for nearly every feature of the Earth's atmosphere, hydrosphere, lithosphere, and biosphere. The electromagnetic spectrum is simply the full range of wave frequencies that characterizes solar radiation. So if you look at this graphic from left to right, the longest to the shortest wavelengths, the spectrum is usually divided into the following sections. On the left, we have radio waves, then microwaves, infrared, visible, ultraviolet, X-ray, and gamma waves. And humans can only see a very narrow band of visible light, which we can see in the very middle, or roughly the middle of this infographic, which is a small fraction of the electromagnetic spectrum. We perceive this radiation as the colors of the rainbow, ranging from violet to red, with reds having longer wavelengths, which is roughly 0.7 micrometers, and violet having shorter wavelengths at roughly 0.4 micrometers. But keep in mind how long these wavelengths really are. I just said that the red wavelength was 0.7 micrometers. Well, 1 micrometer is equal to 1/1,000,000th of a meter, which is approximately 1/100th the diameter of a human hair. It's really small. So for comparison, microwaves, which we see more toward the left of this on the spectrum that we see, are on the order of 1 centimeter long. And television and radio waves have wavelengths even longer, which can be up to a meter and longer than that. So electromagnetic waves can be described by their wavelengths, their energy, and their frequency. And all three describe a different property of light, yet they are related to each other mathematically. It is important to note that the amount of energy in the wave increases as wavelengths get smaller and tighter. So as you move from the left to the right on the spectrum, the amount of energy is going to increase within the wavelength. And you can look at the reflected wavelengths by a sensor and determine the type of material it is reflected from. This is known as its spectral signature. And this premise provides the basis for multispectral remote sensing. And some of these terms might sound new, but I'm going to be explaining them all over subsequent slides. The graph we can see here is showing the percent reflectance on the y-axis and the wavelength from visible to near infrared from 400 nanometers to 800 nanometers. So this is roughly from visible light to just into the near infrared. So in this graph, we're comparing the relationship between percent reflectance and the wavelength of different components of the Earth's surface. So vegetation, as we can see here in broadleaf vegetation and needleleaf, they are the yellow and green wavelengths that have kind of more of a sine wave, where you can see there's like a spike, or not really a spike, but more of a reflectance around 600 nanometers, and then a much higher reflectance around 800 nanometers, which is in the near infrared. So this is a unique spectral signature which enables vegetation, not just broadleaf and needleleaf, but think of any vegetation from agricultural crops to your garden that you like to plant flowers in. All of this spectral signature of vegetation can be distinguished readily from other types of land cover in an optical near infrared image. So for example, the reflectance, as we can see on the graph starting around 400 nanometers, is low, which corresponds to the blue wavelengths. And also in the red regions, which is around 700 nanometers, we can also see a dip in that spectral signature. So these are more absorbing within these wavelengths in the spectrum due to absorption by chlorophyll for photosynthesis. It also has a peak at the green region. And as we go to the right of the graph in the near infrared region, the reflectance is much higher than that in the visible band due to the cellular structure in the leaves. So hence, vegetation can be identified by the high near infrared, but generally low visible reflectances. Property has been used in early reconnaissance missions during war times for camouflage detection. And if we look at snow and ice, which is at the very top of the graph here, we can see reflectance is very high in the visible and the near infrared wavelengths for snow and ice. And for clear water, which is toward the bottom, on the very bottom of this graph, we can see it reflects very little in solar irradiance. But turbid water is slightly higher reflectance due to and can reflect significant amounts of sunlight. And as the chlorophyll content of water body increases, and this can be resulting from an increase in algae or phytoplankton, its blue light reflectance decreases while its green light reflectance increases. So these are just different ways that we can identify different land cover types using spectral signatures from the reflectances from these different land cover types or water body types. And continuing on with the spectral signature specifically for vegetation, and I started talking about this in the previous slide, but I'm going to continue now. So certain pigments in plant leaves strongly absorb wavelengths in visible, specifically red light. And the leaves themselves strongly reflect wavelengths of near infrared light, which is invisible to human eyes. Again, we can only see in the visible spectrum. There are certain insects and other animals that are able to see somewhat into the ultraviolet and some into the near infrared, but unfortunately, humans, our species is unable to do so. But we can build instruments that can. So, but because we can only see the visible light and we cannot see infrared light, the only thing we see is healthy vegetation as green, because it's going to be healthy vegetation is most reflective in that wavelength. But as a plant canopy changes from early spring to late season senescence, these reflectance properties also change. And using mathematical formulas, we can transform satellite data about these wavelengths into vegetation indices. And a vegetation index is an indicator that describes the greenness or the relative density and health of a vegetation, and that can be done at each picture element or pixel in a satellite image. And by transforming this satellite data into these vegetation indices, researchers such as yourselves can create images and other products that give a rough measure of vegetation type, the amount of vegetation, and the condition, so the relative health of that vegetation on land surfaces, and this can be done anywhere on the planet. And ocean color has revolutionized the field of aquatic remote sensing research. So different applications. We were just talking about the biosphere on land. Now we're talking about ocean color. So we're talking about life on the surface of the ocean. And the applications of ocean color remote sensing are extensive and fundamental to our understanding and monitoring of both marine and freshwater ecosystems. So longer visible wavelengths, so green and red, and near infrared radiation are absorbed more by water than shorter visible wavelengths, such as blue. This is why most water looks blue to us. So, or blue-green, if there's phytoplankton or other organisms on the water. But satellites provide the capability to map optically active components of upper water column in inland and near shore and open waters. So the color of the ocean surface is indicative of the ecosystem that lies beneath. Communities of phytoplankton, which are microscopic photosynthesizing organisms, abound in near surface waters and are foundational to the aquatic food web and carbon cycle. Now, this might look like a picture or an image, but every pixel or picture element in this is indicative of different wavelengths, and every single of those wavelengths matters for understanding ocean science. And now we're going to move on to spectral signatures of the atmosphere. So as wavelengths travel throughout the space to our planet, from the sun to the earth and back to a sensor, this is again a space-based sensor, so a satellite in orbit around our planet, the electromagnetic energy passes through the atmosphere twice. Once as it travels from the sun to the Earth's surface, and then back as it's reflected off the surface of the Earth or the atmosphere back to the instrument or sensor, which is orbiting our planet. So it has to travel through the atmosphere twice. And much of the incident energy is absorbed and scattered by gases and aerosols in the atmosphere before reaching the Earth's surface. Passive remote sensing, which I'm going to go to into more detail momentarily, relies upon the concept that light from the sun passes through the atmosphere and contains signatures of everything it passes through. Atmosphere correction removes the scattering and absorption effects from the atmosphere to obtain the surface reflectance characterizing surface properties. So think, the geology or the biosphere, or the hydrosphere. We want, the reflectance unique to those signatures on the planet and not maybe contaminated or by different aerosols and gases in the atmosphere. So the way the electromagnetic radiation spectrum interacts with the atmosphere, satellites can provide information about the atmosphere's composition. This includes the presence of particulates that may contribute to air pollution, clouds, and to precipitation. And as we talk about true color images and false color images, this really has to do with the wavelengths of light in which we're trying to represent the electromagnetic spectrum. So a true color image is designed to display the Earth in the colors like we might see with our own eyes, for example, when we just look out, or if we, say, took a picture with our smartphone from, say, the International Space Station, a true color image would be just that. It'd be what we can capture with our own eyes. And this product is primarily a combination of 3 channels that are sensitive to the red, green, and blue visible light. And in this image that we see on the right, it's a MODIS image. MODIS is an instrument that is on 2 different NASA missions orbiting our planet. And we can see it's a true color image for this, again, red, green, and blue. And these different parts of the spectrum or wavelengths are broken up at 671 nanometer, 551, and 443 nanometer bands, as we can see in the upper left of this image. So for example, in the red image, which is in the upper left, the water is darker, as we can see. Hopefully you can see that if you're familiar with the southern hemisphere. We can see the darker areas are actually the ocean, the Indian Ocean. It looks like it's just off the coast of Madagascar. And the scene is slightly dimmer. The blue image, which is on the far right, is lighter because of Rayleigh scattering in the atmosphere and other interferences with the atmosphere. And the values that represent the cloudy areas are actually, in all 3 images, very similar, because scattering by clouds does not depend much on wavelength. So visible light does not penetrate clouds. It's highly reflective. So it doesn't matter what visible band, if it's red, green, or blue, it's going to be reflective pretty much uniquely and consistently across those different bands. However, you can see in the red and green bands that that it's absorbing water more than the blue band. So the water looks darker in those channels, whereas if you look at the blue, you can actually see, just like we look at water and we typically see blue water, we can also see that represented in this visual true color image from the MODIS instrument. And when these 3 channels are combined, which is we can see in the bottom of this image, we can now make out bare soil, brown colors, the ocean, vegetation in the equatorial regions of the African continent, etc. And the water also looks bluer, and the clouds still appear white. Now, to wrap your brain around false color images, this took me a little bit of time when I was first learning about remote sensing. So true color images, I feel most people understand. It's, what we can see with our own eyes. But a false color image is really assigning the colors that we can see with our own eyes to parts of the electromagnetic spectrum that we cannot see. So So for example, different wavelengths of light, such as infrared or microwaves, are assigned specific colors, so red, green, or blue, same that we're able to see with our own eyes, to create an enhanced image for analysis. So it's a way of tricking our brain into looking at light that we can see, but assigning those colors to parts of the spectrum that we are unable to see with our own eyes. But we are able to observe and capture using different instruments and sensors on satellites. So the image on the left is a visible true color image. And as we can see, there's a fire burning in this image. And in order to see the area burned, we need to see through the smoke. We're unable to see it because that smoke is very reflective in the visible light. But to do this, we can use longer wavelength channels, such as the shortwave infrared and the near infrared. So the image on the right, especially the area in the magenta, which is that very purplish image kind of more toward the left of that image, it really sticks out. It represents land that has been burned. So if you look back and forth between these 2 images, it's hard to really distinguish that burned area on the left image, but it's very easy to identify it once we start using these different channels, such as shortwave and near infrared parts of the spectrum. And so even though we can see through the smoke, we can still see shades of smoke in the right image as dark smudges. These types of images have very useful applications for land mapping. And to continue further with false color, imagery, in this case, false color satellite imagery, this is a series of Landsat images of southeastern Florida. That's a state in the United States, down in the in the southeast. And this is in southeastern Florida and the northern Everglades, which is illustrate why you might want to see the world in false color. So if we look at the left image, this is a true color image, same as we would see with our own eyes. And we can see a dark green forest. We can see a light green agriculture, which is what is labeled fields toward the top of that true color image. We can see that label. And then we can see brown wetlands, which are kind of in the middle of that true color image. And then to the right of that true color image, we can see more silver urban areas, which is comprising the city of Miami, Florida. And then just offshore in the very bottom right, we can see some turquoise offshore reefs and shallows. And these colors are similar, again, to what you might see if you were passing over this region in an airplane and you took a picture out the plane somehow. But the second image, again, as we're moving into more false color, is going to give us a completely different interpretation using different parts of the spectrum. So, for example, the second image shows the same scene in green, near infrared, and shortwave infrared light. So that near infrared and shortwave, we are unable to see with our own eyes, but we can really start accentuating different land cover types by using these different parts of the spectrum. So in this false color combination, plant color land is bright green. So any vegetated cover, land cover, and water is black, so it's highly absorptive in water land cover. And then the bare earth ranges from tan to pink. So if you look at those urban areas on the right of that middle false color, so basically the built up urban areas of concrete and asphalt, etc., are going to appear more in pink. Now, what's interesting is the newly burned farmland is dark red. So if we look at the top of the image again, this false color middle image, we can see the fields, those agricultural fields. Some of them are not green; they're very red. And these newly burned fields are oh, I'm sorry. And then older burned areas are lighter red. So the newly burned fields are darker, and the lighter burned fields have been burned previously. And much of this farmland is actually used to grow sugarcane, and farmers burn this crop before harvest to remove leaves from the canes. And because the burned land looks different in this type of false color image, it is possible to see how extensively farmers rely on fire in this region for growing sugarcane in this part of Florida. And lastly, if we look to the right image, which is the image which is clearly the reddest of all three, this false color view also reveals how water flows through the northern Everglades. So plants are dark red because they reflect near infrared light strongly. So I think I mentioned that in the previous slide on vegetation, and especially healthy vegetation, that the pigments in vegetation absorb strongly in red, but they reflect very strongly in healthy vegetation in the near infrared. But because we are assigning the near infrared spectrum and we're assigning the red color to it, anything that's healthy red vegetation is showing as red in this false color image. And plants that are growing quickly reflect more infrared, so they are brighter red. And that means this type of false color image can help us see how well plants are growing and how densely vegetated an area is. And similar to the middle false color image, water is black and blue, and urban areas, including Miami, Fort Lauderdale, etc., are silver in this image. So really cool ways of using assigning different parts of the spectrum to wavelengths of light that we can intuit because we see everything through visible. And now I'm going to transition a little bit to satellites and sensors and give a brief overview on how NASA builds missions and puts different instruments on these different spacecraft buses. So most of the data that we use at NASA, and hopefully the data that you're currently using, and if not, hopefully soon using, comes from the Earth-observing satellites, which carry one or more sensors or instruments. And when I say sensor or instrument, you can use those interchangeably. They mean the same thing. Some people are more used to hearing sensor, some are more used to hearing instrument, but just know when I say them, I'm referring to the same thing. Now, the image on this slide is of the Landsat 9 spacecraft with two of its sensors, the Operational Land Imager 2 and the Thermal Infrared Sensor 2. And as the name implies, this is the ninth Landsat mission in a series adding to over 50 years, half a century of free and publicly available data from the Landsat mission. This is the longest data record of Earth's landscapes taken from space, and it's all freely available to anybody at any time. Since the launch of the first Landsat satellite in 1972, the mission's archive has grown to contain more than 8 million images. And you can see here that the spacecraft bus is what we're referring to as Landsat 9. And then on that bus are these different instruments that are being attached to it to collect the data as it's orbiting our planet. And the following slides are going to go into more detail on some of satellite characteristics from orbits to different resolutions, as well as some of the applications that we can derive from these different observations. So an orbit, in its general sense, is a curved path that an object in space, such as our planet, the moon, like our moon orbiting our planet, or a spacecraft, in this case a satellite, takes around another object due to gravity. So upon launch, a satellite or spacecraft is most often placed in one of several particular orbits around Earth. Satellites in geostationary orbit, which is what we're seeing in this animation or this visualization here, they orbit Earth around the equator from west to east, following Earth's rotation by traveling at exactly the same rate as Earth's rotation. This makes satellites in geostationary orbit, or GEO, to be stationary over a fixed position. In order to perfectly match Earth's rotation, the speed of geosatellites should be about 3 kilometers per second at an altitude of 36,000 kilometers, which is what we currently see in this visualization. This is much farther from Earth's surface compared to many satellites. Now, GEO is used by satellites that need to stay constantly above one particular place over Earth, such as telecommunication satellites and meteorological satellites, where we need near real-time information on weather. This way, an antenna on Earth can be fixed to always stay pointed toward that satellite without moving. It can also be used by weather monitoring satellites because they can continually observe specific areas to see how weather trends emerge on any part of that planet. Now, satellites in GEO cover a large range of Earth, so as few as 3 equally spaced satellites can provide near global coverage. This is because when a satellite is this far from Earth, it can cover the entire disk of the planet in one image. At low Earth orbit, as the name suggests, it is an orbit that is relatively close to the Earth's surface. It is normally at an altitude of less than 1,000 kilometers. And in GEO, I mentioned it's around 36,000 kilometers. So all of these satellites in low Earth orbit are going to be less than 1,000 kilometers from the surface of the planet. But it's still very far. By comparison, most commercial airplanes that don't fly at high altitude, so if you're just flying from one continent to another, they don't go much greater than roughly 14 kilometers. So even the lowest LEO is more than 10 times higher than commercial airlines. So unlike satellites in GEO that must always orbit along Earth's equator, low Earth orbiting or LEO satellites do not always have to follow a particular path around Earth in the same way. Their plane can be tilted. This means that there are more available routes for satellites in LEO, which is one of the reasons why LEO is a very commonly used orbit. As we can see here, we see in this visualization orbits around the equator. We can see some that are more an inclined orbit and some that are more polar orbiting. So they're passing from south to north over the both poles. So LEO's close proximity to Earth makes it useful for several reasons. It is the orbit most commonly used for satellite imaging, as being near the surface allows it to take images of higher resolution. It is also the orbit used by the International Space Station, as it is easier for astronauts to travel to and from it at shorter distance. Satellites in this orbit travel at a speed of around 7.8 kilometers per second. At this speed, a satellite takes approximately 90 minutes to circle or orbit the Earth, meaning the International Space Station, or ISS, travels around the Earth about 16 times every single day. And I'm a little jealous because I love watching sunrises and sunsets. And if I could get 16 sunrises and sunsets every day, let me tell you, my quality of life would be higher. So satellites in polar orbits usually travel past Earth from north to south rather than from east to west, passing roughly over Earth's poles. Satellites in polar orbit do not have to pass the north and south pole precisely. Even a deviation within 20 to 30 degrees from that pole is still classified as a polar orbit. Polar orbits are a type of low Earth orbit as they are at low altitudes between 200 to 1,000 kilometers from the surface of the planet. Now, sun synchronous orbit is a particular kind of polar orbit. Satellites in sun synchronous orbit, or SSO, traveling over the polar regions are synchronous with the sun. So what does this mean? This means they're synchronized to always be in the same fixed position relative to the sun. So that same sun angle from the satellite as it's collecting reflectance off the surface planet, it's always going to be in that same fixed position because it's been synchronized. And that means the satellite is always going to visit the same spot at the same local time. So for example, if a satellite passed over the city of Paris every day at exactly noon, and that's what sun synchronous orbit means. And the satellite will always observe a point on the Earth as if constantly at the same time of the day. And this serves a number of applications. For example, it means that scientists and those who use the satellite images can compare how a location or region changes over time. Scientists use images like these to investigate how weather patterns emerge to help predict weather or storms when monitoring emergencies like forest fires or floods, or to accumulate data on long-term problems like deforestation or rising sea levels. And I'm briefly going to talk to you the difference about passive versus active sensors on space-based platforms. Now, passive remote sensors measure radiant energy reflected or emitted by the Earth atmosphere system or changes in gravity from the Earth. The power measured by passive sensors is a function of the surface composition, the physical temperature, the surface roughness, and other physical characteristics of the Earth. Radiant energy is converted to biogeophysical quantities such as temperature, precipitation, and soil moisture. And we provided some examples of different NASA missions, and you can click to learn more about these passive sensors on the link provided. Now, in contrast to passive sensors, we have active sensors, which provide their own energy source for illumination. They are used for measuring signals transmitted by the sensor that were scattered by the Earth's surface or its atmosphere. Most active sensors operate in the microwave portion of the electromagnetic spectrum, which makes them able to penetrate the atmosphere under most conditions, and they can see through clouds. And they can also operate day and night. So passive sensors, because they rely on the sun for energy and the sun's radiance reflecting off this surface, can only operate in the daytime. But active sensors can operate both day and night because they have their own power source, in this case, microwaves. And they have a variety of applications related to meteorology and observations of the Earth's surface and atmosphere. And we've provided some examples of NASA missions as well as European Space Agency missions. And we have a link here provided if you want to learn more about active sensors. And now to cover the theory behind spectral resolution. In principle, surface material on the Earth can be identified from its spectral reflectance signature if the sensing system, in this case the instrument on a platform, has sufficient spectral resolution to distinguish its spectrum from those of other materials. This premise provides the basis for multispectral remote sensing. Resolution depends upon satellite orbit configuration and sensor design, and different sensors have different resolutions. The spectral resolution signifies the number and width of spectral bands of the sensor. The higher the spectral resolution, the narrower the wavelength range for a given channel or band. I like to think of a spectral resolution is if you have an instrument it's similar to a box of crayons. And hopefully everybody knows what crayons are. They're different coloring tools that one can use to color on a piece of paper. And if you have a multispectral box of crayons, say maybe you only have 10, you only have 10 crayons in that box. But if you have a hyperspectral sensor or instrument, or the capability of hyperspectral resolution, you have a box of crayons that is probably over 100 crayons in that box. So you're just able to break up the spectrum into finer and finer detail, which allows for a whole host of different applications and becoming more precise in not only identifying general communities of plants, but you can also start drilling down into, families or species of specific plants. So there's a lot of value in higher spectral instruments. And referring to spatial resolution, this depends upon the satellite orbit configuration, and it also signifies the ground surface area that forms 1 pixel in the image. So it is usually presented as a single value representing the length of one side of a square or a pixel. For example, a spatial resolution of 250 meters means that 1 pixel, so picture element or pixel in an image, represents an area of 250 meters by 250 meters on the ground. And the higher the spatial resolution, the less area is covered by a single pixel. So if we look at the 3 images on the right of the slide, we can see the image in the bottom right shows the same image at, from looking from left to right, we can see a 10 meter, a 1 meter spatial resolution. The middle image is 10 meters, and on the right is a 30 meter spatial resolution. And so that's showing the difference in spatial resolution. And temporal resolution is referring to the time it takes for satellite to complete an orbit and revisit the same observation area. This depends on several factors, such as the satellite satellite swath and the latitude of that satellite. And some satellites have greater temporal resolution because they're able to maneuver their sensors, or they have increasing overlap at higher latitudes. Now, the image in the upper right shows a radar image path from NASA's SMAP satellite, where areas at high latitudes are imaged more frequently than the equatorial zone due to the increasing overlap as the orbit paths come closer together near the poles. And the table on the bottom left shows the different satellite sensors and their revisit time. So we talked about the Landsat mission earlier. We talked about the MODIS instrument, and then also some of the commercial. And these are some of the revisit times or the temporal resolution of some of these different instruments and how often they're able to collect data. And I'm not going to go into too much detail, but this is the different processing levels in which NASA processes the images and the data that it collects from these different platforms in space. And so NASA takes the data from satellites and processes to make it more usable for a broad array of applications. There is a set of terminology that NASA uses, and for level 0 and 1, these are different products or processing levels. This is the raw instrument data that may be time referenced. So it records the time that the observation was collected, but it's also the most difficult to use. Levels 0 and 1. Level 2 data is level 1 data that's been converted into a geophysical quantity through a computer algorithm, and the data is also georeferenced and calibrated. So, and then level 3, if you continue to process that, is level 2 data that has been mapped on a uniform space-time grid and quality controlled. Level 4 is a level 3 data that's been combined with models or other instrument data. And it's worth mentioning that level 3 and 4 data will always be easier to use because it'll be more calibrated and it'll also be georeferenced as well. And briefly, this slide is providing some of the advantages of remote sensing, is that remote sensing provides information a lot of times where there are no ground measurements. So you can imagine there's a lot of rain gauges, there's a lot of ground measurements for different applications, but that coverage is very sparse, especially in different geographies on the planet. But Earth observations, especially polar orbiting satellites, which have global coverage, are able to cover the entire planet, so irrespective of if there are ground measurements. And remote sensing also provides information, and it's also globally consistent observations, and it can provide direction on where to place ground-based sensors. So if you are maybe areas of the planet where ground observations are sparse, but we're seeing anomalies in the data that we might want to validate that with more ground measurements. And they also provide continuous monitoring of our planet. And Earth system models integrate surface-based and remote sensing observations and provide uniformly gridded, frequent information on water resources and data parameters. And some disadvantages are listed below, such as it is very difficult to obtain high spectral, spatial, temporal, and radiometric resolution at the same time. And large amounts of data in a variety of formats can lead to more time and processing. And applying satellite data may require additional processing, visualization, and other tools. So now that we've gone through the fundamentals section, I'm now going to provide some training samples from the program, which I referred to that I'm part of, the Applied Remote Sensing Training Program. And I'm also going to show a couple case studies. So I'm not going to go into all the details on these besides saying that we have a long catalog, a long list of trainings specifically for the applications of air quality. And these trainings are they can be applied globally. So regardless, irrespective of your country of origin, where you currently live, or regardless of the domain or the geography in which you want to do your analysis, these data sets are freely available and they are global. And these trainings will walk you through how to access the data, where to access the data, how to do a level of analysis using open source and open access tools. And all of these trainings, again, are free. And even if you don't take a training when it's being conducted live, all of the materials and the recordings from these trainings can be documented and accessed from the ARSET training page. So if you're looking for any training on air quality, or if it's water quality that you're most interested in, if you are doing research, or if you are maybe working from an agency what is being tasked for maybe water quality monitoring, freshwater or ocean, we have different trainings on this. We have different ecosystem focused trainings, everything from coastal ecosystems or to trainings that work with hyperspectral data, and also how to generate these different spectral indices, some which I referred to earlier in this presentation, but these indices can be applied for assessing health of both land and aquatic surface areas. And we also have a long list of agricultural focused trainings as well. And this, what I'm showing on the slide, is but a short list. It's merely a sample of all these different trainings in these different application areas. So what I'm really hoping that you'll do is, as you're looking at these different titles of these different trainings, you're seeing that, for example, here in the climate, you can go to the ARSET website, which we've provided links for in this training. And hopefully you'll have access to the slide deck after I'm done presenting. But the point being, I hope that you'll go there, and if you're interested in any of these thematic areas, that you'll be able to find those trainings. And the other great source is, and I've already mentioned that NASA is committed to open science, and NASA empowers a collaborative scientific process through the open sharing of data and knowledge. And hopefully throughout this, Space Apps Genius Summit, this really has been the mantra for what you've been hearing from a lot of the folks at NASA, that everything that we provide is open science, and it's open source, freely available, data and the tools that we use through NASA that provides are also freely available. So our open data services and software policies ensure that data are freely available to any user for any purpose. And the link that we've provided on this web page, on this the slide right here, is for the NASA Earth Data Search, which is a web application that allows you to search, discover, and access Earth observation data made available by NASA and other interagency and international partners. So depending on the area of interest, the time period of interest, and the mission and data that you're looking for, you can find all of that in this one-stop shop by going to Earth Data Search, which I highly encourage all of you to check out following this workshop. And to access any of the data, it is worth mentioning that you will need to register for a free Earth Data account. I want to emphasize this is a free account, and this free account not only will get you access to Earth Data Search, but it's also a single mechanism for user registration across NASA's profile management. So if you're trying to access some of the tools or services that NASA Earth Data that NASA puts out, you can also use that same user registration to access not only getting the data, but also the tools that NASA provides to work with this data. And another great tool that NASA, or visualization platform that NASA provides, is Worldview. And it offers the capability to interactively browse over 1,200 global full resolution satellite imagery layers and download the underlying data. And some imagery is available in near real time, or within 3 hours of observation, you can get it from NASA Worldview. So it's a really low bar to entry for those that might not be familiar with some of the tools or the software, or might not have the coding skills to be able to access some of the data. This is a very easy way to go on a website, and there's a graphical user interface to start interacting with these different layers. And momentarily, probably in about 5 or 10 minutes, we're all going to go on Worldview, and we're going to start playing around with some of these different layers so you can interact with Worldview yourself and start getting accustomed to working with these different NASA data sets. We've also provided a link to NASA Worldview, so hopefully you'll be able to do that. What I'm going to do now is I'm going to play a video from an ARSET training that will hopefully provide some more background on NASA Worldview.
If you haven't worked with satellite data before, I would recommend starting with Worldview. This is an online interactive browser which allows you to easily display many different satellite remote sensing data products. Its main focus is to provide quick access to near real-time satellite data. Some data sets are updated in Worldview within 3 hours of the observation being made. When you open up NASA Worldview, this is what the interface looks like. You'll see, to start off with, there's this Welcome to Worldview with some examples of different satellite data sets you can use and look at in Worldview. If you're new to Worldview, I'd encourage you to take a look at some of these examples. I'm going to close out of this right now and just show you what the interface looks like. So you can see in the background here, there's an image of the Earth with some coastlines showing up, as you can see here. And the color imagery is from the true color imagery from the Terra Modis instrument, which is you can see here. I can use these buttons here to toggle different layers. So for example, I can turn on the SWOMI NPP VIIRS instrument, and that's what that looks like here. Or the NOAA 20 VIIRS instrument, and that's what that looks like here. So that's these layers on the left-hand slide. I'll go back to those a little bit later. On the bottom, this is the time slider which I can use to scroll backwards and forwards in time. You can see as I scroll back in time, different satellite data is being populated there. I can also use these date selector here to select the date of interest. And then I can pan and zoom using either my mouse controls, clicking and dragging to pan, and using my mouse wheel to zoom. Or on this side of the screen, there's buttons related to zooming in and out. Also in the upper corner of the screen here, there's information on the tool, which you can click on there if you want more information. And if you, in particular, if you click this Explore Worldview button, this brings up the introduction again. So just to show you how I might use this tool, I'm going to scroll back to a major air quality event that happened in my area, the northeastern US, on about June 6th, which was when the northeastern part of the United States here was impacted by wildfire smoke from Canada. And you can see in the true color imagery, which is shown here, you can even see this impact right there. So you have the wildfires taking place here, the smoke coming off of those, more wildfires here with the smoke coming out. And you can see the very dense smoke clouds over New York there and the northeastern United States more generally. If we want to look at some of the data products I've discussed today, we would use this Add Layers button to add new layers. So if I click on this, it brings up a menu which categorizes different types of satellite data sets into these different application areas. And you can see air quality is front and center here, which is really nice. Let's look at the aerosol optical depth. So if I pull down this aerosol optical depth menu, you'll see some of the instruments we talked today, the MODIS instrument, the VIIRS instrument. I'm going to go to, let's see, maybe Aqua and Terra Modis combined aerosol optical depth products. This is one of the data products available. You'll see if you scroll for Aqua particularly, you'll see deep blue algorithm, the dark target algorithm I mentioned. We'll just stick with this combined just to illustrate what this looks like. close out of that. So you can see what this data product looks like here. You can see the aerosol optical depth scale here, and I'm just going to use these options to pick a different color scale just to illustrate what that looks like. So you can see this imagery here, the areas of high aerosol optical depth where there's very dense smoke. And you can even see the interference that smoke, the densest parts of the smoke, are causing with these retrieval algorithms, where we're not even able to retrieve aerosol optical depth in some of these very dense smoke areas. You can also see that clouds are having a similar effect in a lot of areas, blocking the aerosol optical depth information. But even so, we're picking up on some areas of very high aerosol optical depth. Just to illustrate another example of this, I'll bring up another area. I can also bring up, using this menu, the fires and thermal anomalies here. And I'll pick the Aqua and Terra Modus fire and thermal anomalies product. I'll check that, close out, and you can see these orange dots which have shown up, indicating the locations of fires detected by the satellite. So you can really see how you can use this tool to overlay a lot of different data sets and just get a broad look at what the data is telling us in terms of information about air quality, fires, and various other things that we might look at.
Okay, so now with I know that we're quickly running out of time, but there are a couple things I want to do. So for the next 5 minutes, okay, I'm gonna drop a link in the chat here, and I'm hoping that everybody's going to access this. So everybody should have a link to the NASA Earth Data Worldview. And what I want to do now is have everybody go to that, the link that I just provided. I'm going to give everybody a second to get there. And I'm going to start sharing my screen again. And hopefully everybody can see my screen. Yes, hopefully. If not, please just let me know. So the first thing everybody's going to see, if you're following along, and hopefully you all are, with the link that I provided in the chat, is the landing page for the for NASA Worldview. We can see in the landing page that there are a lot of different kind of case studies that you can see. You can see, like, if you want to look at a kind of a case study for atmospheric rivers or surface water extent or El Nino impacts around the world. We also have the night lights from NASA's Black Marble. So I would like, what I'd like to do now, before we let you explore some of these different case studies, is we're actually going to close out of the worldview, and we're going to go onto the base layers, and we're going to change that base layer to this top one. We can see this corrected reflectance NOAA 21 VIIRS. We're actually going to show that layer and turn off the MODIS layer. So hopefully, if you're following along, we have the NOAA 21 VIIRS base layer turned on. And what we're going to do now is we're going to go up to this search search option at the top of the screen, and we're going to type in Los Angeles. And once you start typing, it should auto-populate. And we can go ahead, once you type in Los Angeles, there's going to be a number of options that are going to come up. And I want you to click on, it should be the first option, Los Angeles, California. And by searching for that, we will zoom into Los Angeles, which is a city in Southern California. And once we've zoomed into it, I'm going to just go ahead and remove that map marker, close out of it. I just want to be in the general geography of the area of interest, because we're going to take a look at the devastating wildfires that burned in Los Angeles in early January of this year. So to get to that date, we can do two things. We can use this time slider and move back in time, but I'm just going to go ahead and go to the bottom left of worldview, and we can see we have different options for year, month, and day. I'm going to keep the year the same at 2025, but I'm going to change the month to January, and then I'm going to change the day to January 7th. Hopefully you're all following along. And you can also do this with the time slider as well, but I will leave this up to you whether you want to use the time slider or you want to change these parameters using the year, month, and day options in the bottom left. And we can see here, we have one fire, what looks to be a fire burning just in the Palisades area of the Los Angeles County. Now, to highlight the fires, we want to go to this red button because we want to add more layers to be able to visualize the layer on this base map. And this base map being this NOAA 21 VIIRS instrument or image that was collected. So to add that layer, we're going to go to this red button. Hopefully you're all following along. We're going to click on Add Layers. And what I want to do is I'm going to go to Fires. There's many different layers that you can add. And the good thing is, on your own free time, I want you to come back and explore these different layers. You can see everything from smoke plumes to vegetation, severe storms and floods, drought, if you're interested in drought, dust storms, air quality, if that's your research or your area of interest, your application area. But for this example, I want you all to click on fires, and we're going to see that we have a number of different layers that we can add to our map view. And what I want you to do is I want you to go to the fourth layer down, which is the fires and thermal anomalies. Hopefully you're all seeing that, fires and thermal anomalies, and I want you to click on that. And then you have 3 different radio boxes to choose from using the Aqua and Terra Modus. And I want you to click on the top option, which is fires and thermal anomalies, day and night. And now we can close out of the layers by using this arrow in the top left of this window. And now I want you to close out of this layers. And now, hopefully, if you're following along, we now have on the left-hand side of the worldview, we have a layer for fires and thermal anomalies from the Terra and Aqua Modus instrument. Modus is an instrument I referenced earlier in the presentation. And if we zoom in, we can actually see these thermal anomalies corresponding to the Palisades fire, which was burning on this date. So now we can start mapping these different and visualizing these different layers. Now I want you to start progressing forward in time. And again, you can use the time slider to do this, but I'm going to advance daily so I'm going to go to January 8th. And you can already see by the next day, we see way more thermal anomalies, and we can also see the visual image of the smoke from this Modus instrument from not only the Palisades fire, but also in other fires surrounding the Los Angeles basin. And we can see that this fire, which originally started on January 7th, just in the Palisades area, due to extreme dry conditions and extreme windy conditions, this fire quickly spread and got out of control in other areas, much to the devastation of the communities and the life in generally living in this part of the planet. And if we advance even more, on January 9th, we can see that again, yes, these fires were continuously burning due to these thermal anomalies that we can detect using satellite imagery and also using visual imagery to capture these. So this was just a quick demonstration. Hopefully you're all following along. What I want you to do now is go back up to the top left of the window and click on Worldview to reset the defaults. And if you're prompted, just say OK. And this will bring you back to the landing page for NASA Worldview. What I want you to do is using these different case studies, I want to give you a couple minutes to explore if it's nighttime lights from NASA's Black Marble, or if it's assessing floodwaters, or if you're interested in like an introduction to worldview. I'm going to give you all a few minutes to choose one of these and explore it. And don't be afraid to turn off different layers on the left-hand side if they're base layers, or layers that you're adding. So in this case, I'm going to click on the night lights from NASA's Black Marble. But again, you can choose any of these. And again, this is from February 6th, but I can change that date to February 7th. I can use the time slider. Maybe I'm more interested in something from, say, February 20th, etc. But I just want you to interact with these different layers, zoom in and out. You can check out these different sliders showing exactly what the data is portraying. You can turn these layers on and off. If you want to add more layers to that, feel free. But this is really your time to really explore any of these different case studies and layers that are in here. So we're going to give you all 3 minutes to do so, and then we're going to wrap up the presentation and go to the question and answer. So you have 3 minutes to explore worldview, but again, we're hoping that all of you will revisit worldview and explore more of NASA data sets that you all have access to anytime, freely available, and these are all available for download as well. So again, we're going to give you 3 minutes to explore worldview.
Sean, I know our participants are diving into NASA worldview. A quick question. There's so many different types of data, different formats. Which is best for a beginner, or which is the most? Or I think Tara asked in a question in the chat here. Which is your favorite to start with or to look at? Are you still muted, Sean?
Yeah, great question. So if Tara, if you're looking for, are you looking for any specific type of data? Because if that's the case, we can certainly point you in the right direction. Parker, can you maybe elaborate on the question?
Sure. I think folks are wondering, between non-visible wavelength or false color images, how to determine when to use which type of data.
Yeah, it really depends on the application. So if you are, for example, if you're working in a more tropical latitude, more tropical geography, there's going to be a lot of cloud cover in this part of the planet. And optical imagery, this is imagery that's collected in visible wavelengths or in infrared wavelengths, are not going to be able to see through the clouds. They're going to be highly reflected. So it depends, maybe if you're looking at maybe flooding or surface change, maybe deforestation in maybe Amazon or something. But to do that, it might be more appropriate to use more active data, so non-optical data, because you'll be able to gather data every day, regardless of weather conditions, night or day. And that might be a good advantage in that type of geography. But if you're looking at an area, and again, it really depends on the application, but if you're looking for more air quality data sets, then we can certainly point you in the direction on where to get that data and how to work with it. Or if it's working with optical data for agricultural monitoring or agricultural crop classification, then it really depends on if you're trying to look at like a daily scale, or if you're trying to see more of a phenology in that, and like when are things greening up throughout the season, when are forests and agricultural crops being planted or greening up early in the season and then senescing later. Maybe you need more high temporal resolution to be able to see that growth curve, or maybe you only need one image per month. Maybe you don't need the granularity in temporal resolution, but maybe you need a higher spatial resolution for what you're doing, because maybe you're trying to drill down to an actual specific crop, not a like an area, but a specific crop. And maybe certainly in certain parts of the country or certain parts of the planet, there are large areas planted, monocultures, but in different parts of the country, there's more subsistence, small scale farming, and you're going to have a lot of different crops intercropped. So you might need a higher spatial resolution, but you're not going to get the temporal resolution. So again, it really depends on what you're trying to do with the data and what that application is. And Tara, I hope that you will certainly reach out to me, and I can point you in a direction if you're looking for certain data sets or an application and how best to use the data. I'm hoping you'll reach out to me personally, because I'm happy to reply and give you more information on that. So, but it really depends on the application that you're trying to do.
Sure. I think it feels right to, I know folks are still exploring a worldview, but I'm going to continue to raise some questions that folks have shared.
Great.
We had another question from the chat about AI analysis.
Yes.
They wonder what data level, 0 to 5, to use in such analysis, and where could we acquire such data?
Yeah, I would say, well, all of the data again can be found through NASA's Earth Data Search, and all of NASA data, not only NASA data, but also some of the partnering agencies such as European Space Agency, as well as others. So all of the data can be accessed through NASA Earth Data Search, but if you are more comfortable using like an API, if you're trying to get lots of data and subsetting it, then NASA provides the ability to use an API to access that data. So there's different ways of getting the data. And then the second part of that question, I think, again, was what, Parker?
How to use it in AI analysis.
Yes, for AI analysis. So there's different tools that are available. Some are freely available, some are proprietary, they're commercial, but there are different, like for example, there are different machine learning algorithms that you can use for, taking a lot of these data sets and drilling down to, if you're trying to monitor a certain crop, for example. I keep going back to the agricultural classification, but there are definitely machine learning AI algorithms that are that different software provides. NASA provides some of the software. Some of them are provided through different platforms, and some of them are commercial, some are not. But there's certainly tools and algorithms that are machine learning that one can use to apply to these different data sets if you're looking at like large time series of data, et cetera. So that we certainly provide that, and again, I would just encourage whoever that person is, really depending on what they're trying to do with the data, I would hope that they would just reach out to me directly, and I can point them and maybe guide them in a more constructive manner than, speaking in general terms right now. Just knowing what they're trying to do with the data and what data they're looking for, I can certainly help guide them more constructively.
Awesome. Time for one last question, Sean. Are there upcoming or future projects that you're excited about that are using this ARSET data?
Yeah, we actually have a training starting next week, which is focused entirely on landslides. So how to automate landslide mapping. So a lot of this is, again, getting to machine learning algorithms to take optical data and as well as SAR data. So this is non-optical data, and using both manual and automatic machine learning algorithms to monitor landslides globally, which is obviously of very high interest for people that are, maybe we don't have boots on the ground per se. We don't know, we don't have maybe, we don't know the impact of some of these communities because they might be living in an area where they don't have reliable internet or cell phone connection. And so being able to map these landslides and also assess the damage associated with these landslides in near real time is of great value to people trying to manage disasters and support disaster relief. So this training is going to be starting next week, and we hope that folks that are on this call will certainly join us for that. And Parker, it's up to you. I do have some wrap-up slides, but if we're short on time, I'll just toss it back to you to end it.
I think we're going to share the slide deck with the audience at the conclusion here, so folks will have a chance to look through those wrap-up slides. We do want to thank you for your time, Sean. And thank you for sharing your expertise. This is a wonderful opportunity for folks to learn from you, to learn about how NASA's resources are available to them and how they can get hands-on experience using the Worldview tool. Folks in the chat, please do your best to show some appreciation for Sean, for ARSET, and the awesome work he was able to share with us today. These skills are going to be useful for you as you engage in your own projects, as well as you might find these skills have prepared you for the 2025 NASA SpaceX Hackathon, which is taking place October 4th and 5th. So folks, stay tuned for registration. We are coming close to the conclusion of our Collective Genius Summit programming. As a snapshot reminder, the rest of our programming is as follows. We will reconvene at 2 after a break for our final block. There we continue our theme of building for the future by hearing from 4 NASA leaders in training who are completing or have recently completed their doctoral studies. Then we'll split up, just like we did in this block, with the option for another workshop, this time led by Dr. Becky Bolger from NASA's GLOBE program, to help us learn how to use the Globe Explorer app. Alternatively, you can join a connection session for networking and building relationships, and a link to that session will be provided at the conclusion of the Building Careers panel. For now, we do encourage everyone to take a quick break. Don't forget to stretch and rest, take a walk, refresh yourself however it makes most sense for you. On your way out, please don't forget to take the quick WebEx poll that showed up on your screen. We're so grateful for everybody's time, so grateful for everybody's energy. We'll see you in 1 hour. Sean, thanks again for joining us.
Great, Parker. Thanks so much. Thanks for everybody for joining today. Really appreciate it. Thank you.